So, good evening, all. Good evening, sir. So, we, the NPS Society, is back with another exciting event, a webinar on the topic Development of High Current Thermionic Injector for an Energy Recovery Linac. And I am Kriba Jobi, the Secretary of NPS's Sahrdaya. The Nuclear and Plasma Science Society, NPSS, is the IEEE technical society that covers the field of nuclear science and engineering and plasma science and engineering. So we, the NPS Society, is much delighted to welcome you all to the session. It is your presence which enhances the ambience of the event. So welcome you all. And this session is handled by Dr. Steve Gold. He was the principal investigator for a series of advanced accelerated projects funded by US Department of Energy and holds 6 US patents. He is also the recipient of IEEE NPS Richard F. Shea Distinguished Member Award for his outstanding contribution to the IEEE Nuclear and Plasma Science Society and its Plasma Science and Application Technical Committee. Currently, he is the secretary of NPS's Plasma Science and Application Committee and NPS's chapter coordinator. He is a prominent speaker and well known for his distinguished lectures. Sir, we are honored and grateful to get you here as a speaker of the event. Hearty welcome, sir.
Thank you very much. So shall I begin?
Further ado, I'm handing over the session to the kingpin of the event, Dr. Steve Gall. Sir, please.
Okay, so I need to share my screen, so let me do that.
Okay, sir.
Share screen. Allow, let's see here. Share entire screen, allow, and there we are. Okay, so now let me get to my slides and then I'll get started. I hope everyone can see this now. So I'm very glad to be invited here by the NPSS Student Branch Chapter at Sahrdaya College of Engineering and Technology in Kerala, India, to make this presentation. Good evening to you. It's you're about 11 and a half hours after me, exactly 11 and a half hours, I suppose. So I'm talking to you from Colorado now in the US. And this is my topic, development of a high average current thermionic injector for an energy recovery LINAC. I'm retired from the Naval Research Laboratory, but the work I'm going to describe was carried out there. And of course, I'm here also representing the Nuclear and Plasma Science Society as one of their distinguished lecturers. So let me get started. First step in any scientific presentation is to acknowledge my co-workers. So this work was carried out in collaboration with Philip Sprangle and Antonio Ting of the Naval Research Laboratory at the University of Maryland, and Vadim Jabotinsky of Beamwaves Incorporated and Euclid Tech Labs. So they're responsible for a lot of the research that I'm talking about as they work with me. And most important in some sense, since they paid for it, this work was supported by the US Office of Naval Research, who's also the parent of the Naval Research Laboratory where I was employed. So now going to my other sponsor, since I'm here representing the Nuclear and Plasma Science Society, what is the IEEE NPSS? And of course it's IEEE Day, so it's appropriate to talk about this. We are people working together, utilizing science and technology, expanding industry, and of course furthering the careers of the folks who do this all. Our fields of interest include nuclear science and engineering, such as radiation detection and monitoring instrumentation, radiation effects, nuclear biomedical applications, such as, for instance, PET scans for medical applications, particle accelerators, and instrumentation for nuclear power generation. That's the nuclear side. We also have a plasma side, plasma science and engineering, including plasma dynamics, nuclear fusion, plasma sources, relativistic electron beams, laser plasma interactions, diagnostics, and even solid-state plasmas. My original background, my PhD, was in the area of plasma science and engineering. I actually worked on a nuclear fusion project, but the work I'm going to talk about today is in the area of particle accelerators. So my career spanned both sides of our society. One more advertisement. What is it that the NPSS does? Well, we publish 4 transactions. These are scientific journals, 2 in collaboration with other societies. And our principal transactions that we publish solely are the transactions on nuclear science and the transactions on plasma science. We also publish the transactions on radiation and plasma medical applications, which brings in the medical side of our society. We organize and support many conferences and workshops. Each of our 8 technical committees has an annual or biennial conference that we put on. My own conference from the plasma science side is called ICOPS, the International Conference on Plasma Science and Engineering. And we present numerous technical awards to recognize major contributors to our field. So each of our technical areas has their own set of technical awards, which you qualify for often at the end of your career after making major accomplishments. We publish a newsletter that all of our members receive 4 times a year. And if you're one of our members, you should be very familiar with it. It reaches around the world. We provide online access for NPS members to our publications through IEEE Explore. So through it, you can research anything through our journals or through our conference proceedings. We also support humanitarian projects around the world. And this includes in India, where we have a project, I guess a global project called Smart Village that works on rural electrification in areas that are off the ordinary power grid. We provide opportunities for networking and professional services that can greatly benefit your career. And as today's lecture shows, we also support our chapters and student chapters around the world through our Distinguished Lecturers Program. So finally, to summarize why become a member of the society, members can get involved in the affairs of the IEEE and the NPSS and help direct and further promote our profession. So it is a good career path to be a member. I've certainly been rewarded by my membership in society. And just one more slide on this side of the talk. I'm the NPSS chapter coordinator, so I'm in charge of our chapters program. This is a map of our chapters around the world. We have 25 section chapters, as you can see, spread around most of the world, as well as 18 student branch chapters. This shows boxes around just our student branch chapters. And of course, you're one of them. We have 7 student branch chapters in India, as shown here. I like to use their abbreviations. Here's the Sahrdaya College of Engineering Technology in Kerala province in India. And that's one of our more recent student chapters. Our most recent actually is INSAT in Tunisia, one of our few in the North Africa and the Middle East. Okay, so that's enough about the NPSS for today. I could easily fill the hour talking about our society, but that's not what you invited me to do. So now on to an outline of what I'm going to actually talk about. I'm going to give an introduction to free electron lasers and to energy recovery WinAx, and then explain how you can combine the two into an interesting device. Excuse me. I'm now going to talk about our own research program, which was intended to develop an ERL injector based on a gridded thermionic electron gun. I'm going to describe some of the experimental measurements we made on that gun, including punch length measurements and emittance measurements, and a few others, and how we use that to design an improved injector that might actually be able to do what's needed to build a true free electron laser based on energy recovery WinAx in the infrared, and of course provide a summary. Excuse me. So to begin with, I'm sure everyone has heard the term free electron laser, and perhaps most of you know what it is, but I'll assume to begin with that you don't. So this is the diagram of the essential parts of a free electron laser. In this case, I'm illustrating an amplifier rather than an oscillator. So it starts with input radiation going into the device and comes out with amplified output radiation at the far end. It also includes an injected electron beam. And if the beam is made in an RF WinAx type device, which uses radio frequency acceleration, the beam consists of micropulses. So this is one bunch coming out of the accelerator and into the Wiggler field. The Wiggler field, in this case a planar Wiggler, which means it basically is in one plane, in this case a vertical plane. So it consists of magnets arranged in north-south, south-north, north-south, at a spacing called the Wiggler period, lambdas of wiggle. And if everything else is right, including the beam energy and the beam current and so forth, you can amplify radiation at a shorter wavelength called lambda radiation, lambda sub r here. I'll give the condition down below. So that at the end of the device, the spent electron beam at somewhat reduced energy is thrown away, and the amplified radiation is taken out for some application. So just to summarize the physics, the electrons oscillate transversely in the Wiggler field. Since the transverse variation is vertical, then it means the transverse oscillation is horizontal. And they produce synchrotron radiation simply because you're accelerating electrons in the transverse field. There's a force felt by the electrons called the axial ponderomotive force, which presses on the electrons and can decelerate, accelerate them due to the combination of the transverse Wiggler field and the radiation field. So the superposition of those two fields in this region can bunch and decelerate the electrons to make an amplifier device. The energy lost by the electrons amplifies the electromagnetic wave, and the resonant condition is approximately given by the simple formula lambda sub r is equal to lambda wiggle over 2 gamma squared, where gamma is the usual relativistic factor for the electron, which is simply the electron energy divided by about half an MeV. So as an example, if you're trying to build a device at 1 micron, you can build a wiggler at 10 centimeters spacing and use a beam energy of about 100 MeV, and the resulting resonance condition gives you radiation, in this case, at about 1 1/4 microns. And if you want to build an FEL at a much shorter wavelength, you simply change the beam energy. Of course, you make other changes to the beam properties, such as the current and the brightness. But basically, for instance, if you now go up to a GeV, the radiation wavelength goes down by 2 orders of magnitude down to 10 angstroms. Excuse me, 10 nanometers. And you're now in the X-ray regime, and FELs now operate at still shorter wavelengths, such as 1 angstrom, to do very hard X-ray spectroscopy, diagnostics, and so forth for scientific and technical applications. Okay, so now we've moved on from the FEL now to the acceleration. Typical RF accelerator uses pillbox cells, such as this one shown here. This is a simple cylindrical cavity operating in TM01 mode, so it has axial electric field on the axis. This can accelerate electron bunches moving down the axis, and it's surrounded by an azimuthal magnetic field, as shown here. So for the TM01 mode, the cavity diameter needs to be, in centimeters, needs to be 11.5 divided by the frequency in gigahertz. So for instance, at 700 megahertz, this would be about 10 or 11 centimeter radius. That's the regime we're going to be talking about. So how do you make an accelerator? You take a lot of these cavities and put them in a row with the proper spacing. This shows a pi mode structure where alternating cells have opposite electric fields. If you put an electron in here, it would actually be decelerated if this is the electric field, but presumably you put it in at the right time. If you have acceleration in this cell, after half an RF period, you can have acceleration in this cell, and then in this cell, and you can put any number of these in a row to regressively accelerate an electron bunch up to very high energies. And of course, you can fill every RF period with bunches, so you can have a chain of bunches that you can then inject into a device, where you apply the electrons for any number of applications, including, in this case, for electron lasers. This is the very simple schematic of an accelerator. You have a set of these cells in a row. You have a hole to bring the electrons in, a hole to transit the electrons through the structure. You bring RF in through this vertical column here, and that's also coupled through the structure down the center hole. And this is basically a linear accelerator. Okay, so that's the very simple concept of an RF accelerator. Now we talk about energy recovery of LINAC and how you build a free electron laser based on one. So here's the accelerator we spoke about. But let me start over here with where the electrons come from that you're accelerating. There's an electron gun, which very typically for these sort of device is a photo injector, a laser photocathode gun. So there's a drive laser that shines on a cathode. They're bunches of photons, creating bunches of electrons. They're accelerated by this booster accelerator. This is another little accelerator, up to some ejection energy E sub I. And the purpose of this is to make sure the electrons are relativistic, namely traveling very close to the speed of light c before they go through the main accelerator. Typically, in any energy recovery LINAC, you're using a superconducting electron accelerator. So it's run using a helium refrigerator to operate at something close to 4 degrees Celsius, sometimes even colder. And you're also injecting RF power from klystrons or other devices to maintain the RF field in this accelerator. So the electron bunches come in there, they're injected into the accelerating phase. That means every time they go through a cell, they're meeting the accelerating fields in that cell. So they come out at much higher energy than they went in, and then they're ready for some application. But in this case, because it's an energy recovery LINAC, instead they're bent into a racetrack configuration. So they're bent around using magnets, and then they can go through some experimental structure here to do whatever you're going to do with them. For an FEL, this shows 2 different beam lines that they might be bent into, either an FEL oscillator or an FEL amplifier. So the oscillator, a typical configuration is there are mirrors at either end, like for any laser, and the bunches build up radiation in here, and then the semi-transparent mirror at the output end lets left light out, and this is the output of the free electron laser oscillator. For an amplifier, there's a seed laser. It's putting out bunches of photons. They meet the bunches of electrons, go through the FL amplifier together, and then the amplified pulses come out, and the spent electron beam is bent back around after having lost a small amount of energy, delta E. So now you have E naught minus delta E being bent back into the accelerator. It enters the accelerator exactly 180 degrees out of phase with the original electrons. So when these electrons meet the accelerating phase, these spent electrons meet the decelerating phase of the structure. As a result, they're slowed down, and they put their RF, they generate RF back into the structure that was used up accelerating the electrons. Of course, they can only do part of it, so you have to continue putting RF power in through these klystrons. But eventually, the electrons come back out the other end and are thrown away in a beam dump. And the energy of the beam dump is roughly the same energy they started with here, E sub I minus delta E. So you can get a much higher efficiency to a very inefficient process like an FEL by simply recovering most of the electron energy after you've done with the interaction. Okay, so that's the scheme, and now real devices have been built. This is the first really successful energy recovery LINAC. It was done, it was called the Thomas Jefferson National Accelerator Facility in Norfolk, Virginia, and known affectionately by everyone who worked there as JLab. So this is the JLab energy recovery LINAC. It was used to build IR FELs and UV FELs. In fact, this is their advertisement poster, two frequency, 2 free electron lasers plus broadband high power terahertz. The reason I'm showing this, well, there's several reasons, one of which is to show the real accelerator is a very complicated and very large device. So we start this with a high voltage power supply, driving the original electron gun. The electron gun, that plus the original cryo module here, the original short RF section is the injector. So now we have relativistic electrons going through a superconducting RF LINAC. The acceleration is roughly 15 megavolt per meter. So if you're trying to reach 150 MeV, this is about 10 meters long, 30 feet. I'm used to thinking in feet in some sense. And it's part of a much longer lab. The entire lab is maybe 50 meters long. It's a very large device. Here's the beam dump that the spent electrons go through. This is the bending section. And they have several beam lines here, as I illustrated, but they're all oscillator beam lines. So this is the IR beam line, as you can see here. There's also the UV beam line. They also generate terahertz radiation. But what's most important for the purpose of this talk is to talk about what they achieved at IR wavelengths. In 2006, they produced 14 kilowatts and 1.6 microns in near IR using approximately these beam parameters. So the R frequency is 1.5 gigahertz. That's, of course, built into the structures. These are 1.5 gigahertz cavities throughout the cryo modules. The beam energy was about 150 MeV. The average beam current was about 9 milliamps. A fairly low current, you might think, and it is, as we'll talk about in the next slide. This was achieved by using 120 picocoulomb pulses and repeating the pulses at 75 megahertz. Now, what you should immediately notice is that 75 megahertz is actually 1/20th of the R frequency. So to put that in the way it's often considered, there are RF bunches that accelerate electrons at 1.5 gigahertz, and we're filling every 1/20th of the buckets. Every 20th bucket is being filled by an RF pulse, an electron pulse. The beam power at multiplying the beam current and energy is about 1.4 megawatts. The output power about 14 kilowatts. You can see interaction efficiency of about 1%. And that's typical for free electron lasers in this wavelength range. In fact, as you go to still higher frequencies and X-rays, the interaction efficiency can be a small fraction of this, 0.1% or lower. So the FEL is a very inefficient device, but has a very big advantage. You can build one to satisfy a whole lot of constraints. It has very short bunch lengths, which is great for doing physics. It can have very high average powers, as you can see here, if you can basically simply boost the beam current enough. And it can for ERL at least, it can have moderately high efficiency by simply recovering a lot of the spent energy. And one more point I'd like to make, the last one from this slide. This work was funded by the Office of Naval Research, who have had a long interest in FELs, and one of the reasons for their interest is they've considered the idea of putting an FEL on a ship. Why would you want to do that? Well, the reason is because the Navy, our Navy, the US Navy, is considered putting lasers on ships as a way to defend the ships against attacks by missiles and other things. So the Navy got very excited about this accomplishment. One of the reasons they funded this project, aside from basic research, and they asked the question about whether you could scale an ERL-based near-IR free electron laser to 1 megawatt CW output and use it for Navy applications. Now you might think it's a kind of strange idea to put this very large device on a ship, and it is a strange idea, but the Navy has very large ships, so they considered this as an option and at least worth pursuing by further research. In order to scale one of these up, you have to do several things. Just as a matter of designing such an amplifier, you want to decrease the R frequency to 700 megahertz, which makes the accelerator part of the problem a lot easier. For several reasons, one of which is simple, while larger structure makes it easier to handle bunches, but also if you're working at superconducting accelerator at lower frequencies such as 700 megahertz, you can operate the structure at higher temperature, which makes that part of the problem easier as well. So you can move back up to, for instance, the temperature of liquid helium rather than having to pump helium to get to still lower temperatures at 1.5 gigahertz. In order to get up to higher currents, to get to the megawatt, you need to increase the microbunch charge by about a factor of 10 compared to JLab, and you need to increase the microbunch injection rate by about another factor of 10. And at this frequency, that means filling every RF bucket instead of in this case, it would be every 10th bucket. Also, using an amplifier configuration can reduce the IR optic problem because you're no longer going to melt the mirrors at the end of the cavity if you eliminate the mirrors and simply bring the output through a window. And finally, you need much bigger power supplies, the power of this device, and lots of accelerator engineering R&D. So there was a fairly large accelerator R&D program also funded by the Navy, but we were funded at a fairly low level to do one little problem, which is to look at one method, among others, of increasing the injector microbunch charge by a factor of 10 and the micropunch repetition rate to filling every RF bucket CW operation, which gets the other factor of 10. And that's the program I'm going to talk about. And before I jump into the experimental part of it, let me say a little bit more about the sort of electron beam one needs and the electron gun to produce it. So now we're assuming the electron gun will produce a bunch charge of nanocoulomb. It'll operate at a repetition rate of 700 megahertz, again filling every RF bucket available in the accelerator. The operating regime would be CW. You turn it on and then you turn it off, and during the entire interval, it's producing an average power of 1 megawatt. And the electron gun also needs to produce a fairly small energy spread to do the interaction physics of the FEL itself. So if you look in the FEL wiggler, you need a very small energy spread for resonance to extract energy from all the electrons. And that's given by this one complicated formula that I'm not really going to justify, simply present. Delta E, the spread compared to E, should be related by this sum of the beam emittance. And I'll talk about the normalized emittance later, which is a measure of the spread in the transverse direction of the electron beam, size and velocity spread. E parallel, so this is divided by the beam radius. A longitudinal emittance term, as well as a transverse Wiggler gradient that's related to the beam size and the Wiggler itself, as well as the Wiggler period and the strength of the Wiggler. So some of these basically are controllable by how you build the accelerator after the Wiggler, such as you can trade off various parameters to reduce the beam size to whatever it needs to be, simply compress the beam using accelerator technology. But there's some things you can't change, you can only make worse. In other words, the properties are fixed by what you start with in the electron gun. So one property that you need, and I'll explain as we go on a little more what this really means, is a transverse normalized RMS emittance of less than 15 millimeter milliradians. The other is a longitudinal normalized RMS emittance of 100 kilovolts picoseconds. And at least to finally compress the beam into what's required in the FEL itself, you start with the bunch RMS duration. This is the length of the electron bunch of less than 50 picoseconds. So as we look at designing an injector gun, these are the properties that we start with. This one can be decreased if you start with this length as you go through the accelerator, but basically the emittance can only get worse. That's simply a property of the emittance. So now let me start with laser photocathode injectors, which are used in I guess virtually all free electron lasers these days. Excuse me again. This is a very simple concept. You simply create electrons using laser pulses. And it's easy to make a laser in principle. It can produce very short pulses. If they're synchronized with the RF period, then you can make an electron bunch from a laser photocathode that emerges into the right phase of the RF electric field and get accelerated by this first cavity and on through the device. So laser photocathode has a lot of advantages and some disadvantages. But first, let me show you that it's not exactly a simple device. It looks simple here, but actually it's a very complicated laser. It's mode locked at the RF frequency and synchronized phase locked to the RF of the accelerator itself. It needs a lot of amplification. It needs conversion into UV because UV photons are needed by the photoinjector. Ultimately, it's shined onto the cathode and produce the electron bunches. This is how all the brightest electron beams are made these days, including those involved for X-ray FELs, where they need hyper bright bunches. Instead of milliradians, millimeters, they need microradians and micrometers of emittance, for instance. So the advantages are the highest possible beam quality, the highest possible beam current, and the shortest possible electron bunches, which are great if you're trying to build a very high frequency FEL. But the limitations for an IR FEL are they tend to be limited low average beam current for a number of reasons. First of all, it's very difficult to get a laser that could drive a photocathode to produce high average beam current. Just the limitation of the laser itself and laser technology, and also limitations of photocathode. If you put too much laser power into the photocathode, you simply destroy it. So scaling up to very high current from a photocathode is very difficult. And the second disadvantage, related to this in part, but also for other reasons having to do with poisoning and so forth, is photocathodes tend to have limited lifetime. They need to operate at incredibly good vacuums, and even in those vacuums, they tend not to last forever, which is what you'd want in a CW average device. So that's why there was an interest in seeing whether the alternative of a device that can produce lower brightness could still do well enough to produce the parameters needed for a high average power IR free electron laser. So let's start with design of an RF-gated high voltage thermionic electron gun. This is a standard illustration from Gilmore's book on traveling wave tubes of a Pierce gun, which is the standard gun used to produce a simple linear electron beam at high current density for either accelerator or for a traveling wave tube, for instance, a microwave device. There's a cathode, typically it looks something like a section of a circle. There's a focusing region, that's region 1, where the electrons are produced. Then in region 2, they're reaching the full energy as they reach the anode potential, which is typically a ground potential, and then they're accelerated out of the device in region 3, where the beam is actually used. And what you need for a gated gun is simply, as shown here, to add a cathode to be modulated at whatever frequency you need. And it has to be survive basically near the cathode. Remember the cathode, I haven't said it yet. In order to get emission to the cathode, it's a thermionic cathode. It's typically operating at about 1200 degrees C. And this gap needs to be very tiny because you need to modulate it at a very high frequency. So that's the basic idea. And the first problem is, where do you get a gun like this for this little project that we set out to accomplish? Well, it turns out that there is a device that uses a gun exactly like that. It's called an inductive output tube. This is an illustration of one built by Communications and Power Industry, CPI in the US, for a 500 megahertz IoT. An IoT is an amplifier used for high average current, high average power applications for things like transmitter tubes in broadcast systems. It can produce up to 100 kilowatts or so CW. It can last for a very long time. It runs for years without replacement. It operates at about 40 kV as shown here. And it basically was the one place we could get a gun to do this prototyping experiment without having to design a gun and spend years getting it fabricated and ready for the experiment. So looking inside that device, you find an RF-gated thermionic gun, and that's what's shown here. This is the cathode grid assembly from one of these IoTs. You're basically seeing the outside of the gun, of the cathode, that is. The anode is not shown here, it's cut away, it's been removed. You're looking right at the pyrolytic graphite grid, which is spaced by about 450 microns from the thermionic cathode, which is a dispenser cathode, which means it emits barium to be able to emit at high current density. This cathode in this gun can produce an average current, CW average current, of 3.6 amps. It can be modulated as demonstrated by IoTs at up to a gigahertz and even beyond, and can last for years, as illustrated here. And one other advantage, it's very robust, rugged, it's not subject to vibration damage, it's not subject to easy poisoning, and it can operate at a modest vacuum of about 10 to the minus 7, 10 to the minus 8 torr, where a very high efficiency photocathode might require 10 to the minus 11 or 10 to the minus 12 torr. Extremely good vacuums. Okay, so the idea then is to take that cathode, in fact, take the anode structure as well, and use it to develop a RF-gated, gridded, high-voltage thermionic injector. This is simply a schematic of, a very simplified schematic of it. So we have the cathode, a thermionic cathode, operating at a high negative pulse voltage, RF drive at the fundamental of 700 megahertz, and in order to shorten the pulse, as I'll illustrate in a moment, also adding a harmonic of 700 megahertz to shorten the RF drive pulse that accelerates electrons from the cathode. The electrons then emerge, and ideally, in an injector, would then go immediately into an RF pre-booster cavity, 50 picosecond, 1 amp average current, and be further accelerated. But we're studying the electron gun, so we never put pre-booster cavities on our device. We're simply going to pursue putting a diagnostics here to see what comes out of the electron gun and whether it's suitable to continue on through a booster and into a full accelerator. Just wanted to throw this one in. One little thing we did to make shorter bunches was consider adding third harmonic. So if you know what a sine wave looks like, this is what adding a fundamental and third harmonic together look like at the proper phase relationship. And if you look at when this would emit bunches, this is also a DC bias that suppresses emission unless the RF acceleration is large enough. So you can try to produce bunches during a very narrow fraction of the full RF phase. And that's what's illustrated here. So that's one other thing we did to the gun to try to produce very short bunches. This shows a simple simulation of how the gun would work. So the RF-gated cathode is here. This is the anode structure. This is simply the output, which is where the diagnostic would be in our case. You can see this first snapshot in phase where the electrons are in the process of being emitted, and also some of the electrons in the bunch have been accelerated up to high energy, where red indicates the maximum energy and blue is the very low energy coming right off the cathode. If you look a little later in phase, you can see the electrons in the lead of the bunch coming out of the structure, whereas at the end of the bunch, the last few electrons are now being emitted from the cathode. If you look still later in phase, in the single RF pulse, you can see the cathode is turned off and the trailing edge of the electrons are still drifting down the accelerating piece of the gun. And finally, looking at the end of the RF phase, the end of the accelerating phase, and the beginning of the next one, we're beginning to see the next few electrons emerging and this bunch vanishing off screen. So that's basically how the injector would work. This simulation showed an emits of 33 millimeter milliradians and a charge of 0.4 nanocoulombs total in this bunch. That's the basic idea of how the gun should work. And now let me spend a few minutes talking about our goals and the pieces of the actual experiment. So the goals of the program, as we put together and as our sponsor funded us to do, was to conduct what we call CW relevant experiments. We know the gun is CW relevant itself because it can run true CW for years. We wanted to do experiments using bunched or pulses of high voltage, simply because it made the job a lot easier in our lab. It involved using a modulator that puts out high voltage pulses rather than a big CW power supply that would have taken a much bigger fraction of our lab. So we're doing CW relevant experiments on the existing CPI IoT gun using combined 700 megahertz approximate frequency and third harmonic drive synchronized at 700 megahertz, basically to determine the feasibility of using a similar gun, not this exact gun, but a gun using the same technology as an RF-graded gridded thermionic gun to be the first stage of the sort of injector that you'd need for high current energy recovery LINAC. The experimental program that we could measure the beam properties we could achieve using this gun as we vary the parameters of the gun. We can measure the bunch charge, the bunch length, and the beam emittance experimentally, And the parameters we have to vary are basically the RF drive, first and third harmonic, the gun voltage, and the grid bias of the gun, which is the pressing emission. And finally, as far as the goals of the overall program, to use the results on this existing gun to design a better gun that would be able to achieve what was really required for this particular application, about a nanocoulomb of charge per bunch, a low emittance of 10 or 15 millimeter milliradians, and a short bunch length of less than 50 picoseconds, suitable for RF acceleration. Okay, now the next word slide, and then I'll start just talking about results, are the pieces of the experiment. We use the IoT gun that we bought from CPI, which is just a subcomponent of their IoTs. A high voltage modulator to generate 15 microsecond drive pulses to do the experiment. Again, not CW, but long enough to get into the CW regime of the pulse generation. We purchased a dual frequency 1 kilowatt tunable RF source that was tunable around 700 megahertz of operating frequency plus the third harmonic of whatever the operating frequency was. So these two are locked together with a phase adjust, so we can also optimize the relative phase of these two frequency components and use that to modulate the grid voltage in order to create the microbunched electron beam. We purchased a fast Faraday cup, a specialized one. A Faraday cup is simply the device that has very low inductance and can capture the bunched electrons and use them to monitor the electron pulse length and the total electron charge. So the device is called a Faraday cup traditionally. We had to buy a super fast one, much faster than the normal device, that had 50 picosecond response time. This was specially developed for this program. And we also rented, buying it was fairly expensive, a fast oscilloscope capable of 16 gigahertz response with 50 gigasamples per second of sampling rate of the signal. And this was a way to directly measure the microbunches in the experiment, and I'll illustrate that as well. In order to look at the beam itself, we used a fluorescent target and a digital camera, so we can simply photograph the beam and make sure it looked right, and make sure that anything we did not perturb the beam unduly. And finally, slit-based measurements using a cerium-doped GAG scintillator screen, and again, a digital camera as part of the system to measure the transverse emittance. So those are the components. Now let me show you a schematic of the gun itself. This shows you the really important parts of the gun. So, oops, sorry about that. The gun basically exists, of course, in a vacuum jacket. It has to run in vacuum. So that vacuum jacket is shown here. The gun itself, here's the cathode, the black surface. Here's the grid that surrounds it. There's a heater coil buried very close to the cathode coil to bring the cathode temperature up to, in this case, about 1100 degrees Celsius. And notice the actual gun is a 7 millimeter diameter hole down the middle. It's put in there for purpose of the IoT gun that CPI developed for a few reasons. One, it assists pumping of this region. And second, that an IoT gun often suffers from back bombardment of some fraction of the output electrons being accelerated back into the cathode. So if that happens, they simply go through the hole and don't damage the cathode itself. So those are the reasons the hole is there, but as I'll show you, it's actually a very bad idea for our application. So we'll get into that in a few minutes. There's a coaxial RF feed to bring the RF signal from our RF amplifier source through a coaxial structure and on into the cathode grid gap. This is actually a very bad match, so we have to do some matching in the feed to try to maximize the RF electric field in this gap. There's a grid bias circuit operating at up to a few hundred volts to negatively bias the grid, so it's suppressed the emission. And there's a Rockwell hard tube modulator that produces 35 or 36 kilovolt electron pulses at about a 15 microsecond flat top pulse to drive the gun. And that's how we can do our diagnostics. Okay, so what does it look like in the lab? Here we are. Here's the high voltage modulator. This is the high voltage section of the modulator, and these are the controls. Here's the 16 gigahertz oscilloscope. Here's our dual frequency amplifier. And here's the electron gun. Let me zoom in now. This is the housing of the gun. The cathode exists right in here. And as close as possible to that, we put our Faraday cup, because if you go too far, the bunches begin to spread, and you're not measuring what you really want to measure. And this is what it looks like as a schematic. So here's the gun, and as close as possible, we push up a fast Faraday cup to do our diagnostics. And this is what we measure. So this is the performance of the gun. You see, excuse me, once again, this is advanced. Okay, here's first harmonic only. And you can see a pulse with about 0.9 Coulomb bunch with a full width half maximum of about 400 picoseconds, and RMS bunch width, which is what we're after, 170 picoseconds. And this is what happens as we add third harmonic drive to it. We can shorten it slightly. So now basically we've gotten it down to 157 picoseconds, and you can see that over here. So basically this shows in principle the RF can actually shorten the bunch width. In fact, we look at just modulation like 2142 megahertz. You can see the beam will modulate at that frequency, but at a very low current. So the gun is not really designed for such high frequency, but it will respond at that frequency. And one more thing I wanted to point out here is that you'll notice perhaps that these red dots, which are the baselines of these traces, is lower than the actual measured current. So there seems to be a problem in this operation of the gun, and that there's some current that is not bunched at all, that is proceeding down the device irrespective of the RF bunching that we're carrying out. This shows high voltage data now. Again, you can see the offset. And in this case, by going to the maximum RF power available from the two frequency components and going up to 30 kilovolts, we got about 0.9 nanocoulomb bunch at 135 picoseconds RMS. And that's about the best the gun could do. Next step was to simulate the operation of the gun. That's what we've done here using a Michel gun code. This shows the simulation using the approximate parameters of the actual experiment. This shows what's emitted by the cathode, because the gun code can look anywhere, including at the cathode. And what it predicts would arrive at the Faraday cup, about 0.995 nanocoulombs and about 135 picosecond RMS. And if we simply superimpose that on the output, it does pretty well. So this gives us the beginning of confidence that we are modeling the gun correctly. The effect of higher grid bias, you can certainly shorten the bunch with higher grid bias, but you greatly reduce the amount of charge. So now we've turned up the grid bias. We're down to about 100 picoseconds RMS, about a half a milliamp of current, and down to about 100 picocoulombs. Not too much better than the RF photocathode. And we can go even shorter to a 14 picocoulomb bunch, but clearly negligible at 80 picoseconds RMS. The trade-off is not very advantageous. This shows just looking at using third harmonic to shorten the bunch. So we picked a parameter where we can make the study, simply freezing the peak current at 0.6 amps and adjusting the RF power as shown here and the third harmonic power here. We can start at 112 picoseconds RMS and get down to about 95 picoseconds simply by changing that ratio. But that's as far as we can go. Remember, our target was about 50. So even with third harmonic modulation, the bunch length is much too long for this application, bottom line. We also, in our studies, discovered emission for the central cathode hole. We did that by looking at what the operation of the gun with simply RF and grid voltage. I mean, no grid, no RF. High voltage and grid voltage. So basically, as you turn up the grid, the negative bias, you suppress emission from the gun. And what we traced out were these dots or these little boxes here. And then we simulated that using, again, the Michel gun code. If we simulate emission for just the cathode, we'd expect the gun to cut off completely at something short of minus 70 volts. And instead, it continues on. The only way that can be modeled correctly in the gun was to look at emission from the cathode hole. And this dashed line shows that clearly the gun is emitting from the hole, even though it was not intended to. This is also a problem in IoTs, but less of a problem there because they're simply RF efficiency and not the micro bunch of electrons itself. It turned out we could actually image the emission from the cathode hole. This shows the setup that we did that with. We've added a solenoidal lens, a magnetic lens. We put the beam through a slit to, since we're operating with RF as well in this measurement. And then here's our fluorescent screen. And by adjusting the solenoid lens to the right strength, this is actually an image of the edge of the hole in the cathode emitting electrons. You can see a little halo here of RF emission from the entire cathode. So there really is emission from the cathode hull. And we can also model that using the gun code again. This shows the emission with the central hull, and this shows the emission without the central hull. And you can see that the emission from the central hull is filling in the gap where basically the bunches should have no emission at all. This shows the bunches themselves, and you can see if we turn off the central hull in the code, which is easy to do, it's not so easy in the lab, we can get better defined bunches, and eventually the current actually does go to zero between each other, the favorable phase of each RF pulse. So clearly in our future gun, the cathode hull must be eliminated. We also can image the beam using simple setup, just to see if it looks reasonably uniform. And then we discovered in this experiment that if we turn the cathode heater had a substantial effect on the appearance of the beam. At a typical operating current of 10.7 amps, this is simply to heat the cathode, the beam was fairly distorted. And you can see that here in a cross section, also measurement. Whereas if we turn off the cathode and quickly made a measurement, we got a uniform beam. So one more conclusion was the beam uniformity is pretty good under these conditions, but in the future gun, the cathode would need a compensated heater winding, which is a standard technique, simply not used in the IoT gun, to eliminate the magnetic field at the position of the cathode. It's simply the magnetic field of the heater currents that are distorting the beam as seen here. And finally, I'd like to move on to beam emittance measurements. This shows the setup. So now we have a solenoidal lens to help collimate the beam so we can deliver it to the measurement. We simply can't push this up as close as we'd like. A vertical translator to produce with 100 micron 10 ohm slit, a fluorescent screen again, a mirror, and a digital camera to look at what comes out. The definition of emittance is given here. I promised I would get to that. I'm not going to completely justify this though. So this is the transverse size in the x direction. And these little angle brackets means this is the ensemble average over the beam. This is the transverse velocity in the x direction, again, ensemble average. And evaluating this entire square root here gives you what's called the RMS emittance. And then if you want to normalize emittance, which is actually the property that matters most, you multiply that by the beam beta, which is V over C, the beam gamma, and you multiply this. Normalized emittance is an invariant property of a beam. It can only get worse. The only way to improve it is to basically throw away the electrons that carry that emittance. Another way to look at it, it's called a volume in phase space. How do you make such a measurement? Well, the standard way is you put a pattern of slits, or simply one slit that scans along in front of the beam, and we look at the spread of a slit of electrons as it drifts downstream onto an imaging target. This is basically the standard way electrons are measured. It works very well at high electron energies because the electrons are basically streaming along in a parallel direction, and because space charge is not a big effect. But it's much harder to measure at low electron energies, as I will illustrate in the next few slides. Excuse me, one more time, let me get a drink of water. So this is set up for beam emittance measurements. Because our gun doesn't like to operate, to be brought up to room temp at atmospheric pressure. If you do that, you have to bake it out and then can recondition it. We've added a gate valve in here so we can close off the vacuum when we need to make a change. We've added a solenoidal lens to focus the beam as much as we can to guide it on through the diagnostics. This cross region here with a vacuum pump underneath has a movable slit moved by the positioner. This has the YAG screen. Here's a viewport, a mirror, and our digital camera to make the measurements. And this is a phase space plot of the slit emittance measurements. So basically, at each Y position from the center, we're measuring the transverse angle at the top and the bottom of the image downstream from the slit. And we get this fairly sloppy looking pattern. We can evaluate it numerically, and this comes out to the 11 millimeter milliradians, which sounds fairly good. Remember, our target was 15. But next step was to see what effect the magnetic lens was having. This one can do experimentally. So here was, I'm not showing zero solenoidal current, but this simply shows what happens as we crank up the current. The emittance actually increases for a while and then falls off at the far end. And we have to understand the reasons for this. Once again, we turn to simulations. So this is a simulation of the bunched beam with and without the solenoidal lens turned on, in this case, at 1.65 amps. And this shows the emittance as a function of position down the experiment, and the charge left in the bunch is a function of position. What we see is, before we even get to the lens plane, we begin to lose current. Position 1 is where we begin to lose current. Some of the beam is hitting the wall. We simply can't get close enough to capture the entire beam. And in essence, as we begin to throw away current, we throw away the emittance that's associated with that current, so the emittance begins to drop. And then as we get into the region of magnetic field, another thing you can do in any device, including an accelerator or a magnet, a focusing lens, is make the emittance worse. If you make non-adiabatic changes to the transmission of the beam, the emittance can actually get worse. And that's what you're seeing happen here. Here, the emittance continues to go down as you lose more and more current, as shown here. But if you go through the focusing lens and you turn it up too high, you pump up the emittance, as shown here, and you end up measuring a much higher emittance than the remaining electrons would otherwise have. And you're back up to something like the starting emittance. So basically, you can't trust the measurements. The true emittance of the beam is much higher than the measured value, and is, of course, too high for the application we're after. So, as I explained at the start of this part of the presentation, our goal was to see what this gun could do and then figure out how to do better with a gun designed just for this purpose. So the first step was to play with simulations, play with the shape of the gun, play with the size of the cathode, the current density, and so forth. And ultimately, this optimized high-voltage electron gun was produced. And these are some of the parameters of it. Again, very similar to the operating parameters, although we've adjusted them a little bit. And the existing gun is predicted to have these parameters. And again, this corresponds to the actual experiment. The modified or optimized gun would be able to produce a nanocoulomb, but it can only shorten the bunch length to 100 picoseconds or so compared to the 50 we were after. And the transverse emittance was still, instead of about 50, was down to about 30, but still higher than the 15 we were really after. So this created a problem, but it also created an opportunity for us to do further research. And we came up with a new approach. And my last few slides will talk about that. This is the design of an RF-gated, rather than a high voltage, we're now using an RF-powered thermionic electron gun to power the high voltage, high power free electron laser. So we've basically gotten rid of the high voltage bias on the gun, which is an important limitation because you want to accelerate the electrons as fast as possible to get good emittance, but there's a limit to the high voltage you can apply to the gun without the gun breaking down. In fact, our original gun runs at DC high voltage, or in our case, 15 microseconds high voltage. If you up that too far, you simply will break down the gun. But you can put much higher RF fields on the gun than DC high voltage fields. So the idea was to basically eliminate the high voltage, and now we put the cathode structure with some modification right up against the first RF cavity. So we're driving the gun the same way as before with the first harmonics. The grid is over here, again, a pyrolytic graphite grid. But now we're moving right up to that, an RF cavity with an independent RF drive. So you can adjust the phase of this drive, and it's a much higher power drive compared to the phase of the grid. The grid separates the two RF regions. There's a focusing shape you can shape the RF electric field by the shape of the first cavity, and this beam would then come out of the exit. This shows a cutaway view. Remember, way back at the beginning, I talked about how big a cavity needs to be. At 700 megahertz, the cavity is 16.4 centimeter radius. So this is about 30 centimeters across. This is the gun region shown here, and this is the output into the next RF cavity. After carrying out the research, we actually patented this gun. So this has a US patent, as shown here, and if you like, you can look up that patent online very easily and see a fuller description of this gun. But I'll show you a little bit more about it over here. So this, again, shows the geometry, and this shows a close-up of the geometry. So there are grid wires basically separating the two regions, putting the bias on the grid to suppress emission, and also the RF is fed in through here, through the coaxial drive, and then the higher field RF is from the RF cavity, and here's the beam exit. And I guess I don't need to discuss all the details here. Of course, this is the axis symmetry. This is one half of the gun. This is the characteristic the electron bunch is predicted again by the gun code, which I'd like to say we benchmarked by comparing it to the real experiment that we did. So this shows the electron bunch being produced and accelerated by the RF field and coming out 450 picoseconds later. This is simply the RF advancing as we go through 2 pi of phase. So the bunch charge is 1 nanocoulomb as desired. It's actually producing a mean energy of 120 kilovolts rather than the 35 we were after, at a bunch length of about, well, a little bit less than 50 picoseconds, and admittance of a bit less than the 15 millimeter milliradians we're after. And I don't need to go through these exact drive conditions, but these were adjusted to optimize the pulse as you do in any design of a new gun. So basically, this is the gun we believe could actually do what we set out to accomplish. And let me summarize that. So we carried out experimental tests of a 35 kilovolt gridded thermionic electron gun, an existing CPI IoT gun, to see what its potential was as the first stage of a high current ERL injector. And we showed that it could produce nanocoulomb at 35 kilovolts, but could not meet the pulse length and admittance requirements that we really were after to be able to replace a thermionic, a photocathode injector with a thermionic injector in a high average current application. We simulated the measurements with the gun code. We produced a gun model on the code that was benchmarked to the actual experimental results and matched them very well. And then we used that as a simulation model to design a new type of RF gun that involved direct RF acceleration of electrons rather than using DC high voltage on the cathode anode gap. This patented RF gun design appears to be capable of meeting the requirements we set out to achieve for a high current injector for a megawatt class IR FDL, including high average current, an amp or so, high charge per bunch of a nanocoulomb, sub 50 picosecond bunches, and a normalized transverse emittance of less than 15 milliradians as we set out to achieve. And basically, this is the end of the experiment. We would have liked to continue on, but about this time, the Navy decided that perhaps putting a free electron laser on a ship was not their highest priority. In fact, they are still considering putting other kinds of lasers on ships, but much more compact lasers like fiber lasers. So they basically decided that this program would not continue, and in fact, in a few years, they also turned off the large FEL program at JLab. However, energy ERL-driven FELs are still a thing. In fact, there are at least a half a dozen of them around the world now in various places in Germany, in the US, in Japan. Basically, they're used for various experiments, including FELs, also high energy physics. And they all use laser photocathode injectors because this application is particularly for high current rather than the much lower current they operate at, and for the requirements of an IRFEL rather than the requirements, for instance, for high energy physics. So that was basically the success of the program in producing a design to do the job, and that was the deliverable for what we were funded to do. Unfortunately, even though we eventually actually bought a modulator and an IoT to drive the next stage of the experiment, this is as far as the experiment went. So that's basically the end of this talk, at least the phase where I don't answer questions. And thank you very much for listening, and I'm happy to answer any questions. And now I'm going to stop sharing my screen so that I'm going to try to stop sharing my screen. There we go. And I should be able to see questions that you might ask. Well, I'm hoping I'll stop sharing the screen. There we go. Okay, so I'm back, and I'd be happy to answer any questions.
Thank you, sir. So participants, it's Q&A section now. You can put your questions in the chat box. Yes, okay. There is a question, sir.
I see the question. It says there are thermionic injectors.
There is a thermionic injectors and photocathode injector. Which one is better and why?
Okay, so Photocathode injectors are the absolute state of the art, producing very high brightness beams. They can produce very high current density because you can simply use a very high photon density on the photocathode in a very short pulse. They produce very high current density, very short pulses. And if you're trying to operate at very high beam quality, at very high frequency to make an X-ray FEL, for instance, the photo injector is absolutely the only way to go. Thermionic injectors are basically an aspect of RF gun technology that can produce very high current, can produce bunch beams modulated at an RF frequency, and that's of course why they were developed as an IoT gun, for instance, for a real application. But they do not scale much beyond the parameters we were after in this case, which was 50 picosecond bunch length. So that's a real limit. You can't get shorter bunches just by RF modulation, but you can get very high bunch currents, very high bunch charges. It's a very robust, rugged device. It's not subject to vibration. It's not easily damaged. So it's a real advantage for other applications, but not for most energy recovery Linux. It might have been ideal, though, for this particular one that the Navy proposed to build. That's it. What was the total cost while the experiment was completed? Well, the total cost of our experiment, I think, was about $300,000, about 300K over a few years. Our terms are a really small experiment. It basically used fractions of people's time rather than full time. And people are very expensive, at least in the US they're very expensive, particularly when you add laboratory loading, which is the cost of running the entire Naval Research Laboratory, which part of which goes down to the cost of people who work at the lab. Now, the cost of the JLab FEL was tens of millions of dollars. If you're trying to build a big facility, it does cost big amounts of money. The experiment lasted in total about 3 years as a part-time project. From when we got funding to when we modified our modulator, purchased the electron gun, purchased the RF power supply for the device, that took about the first year, simply to get everything in hand. And then we spent something close to 2 years doing the experiment. I might have already answered this, that the advantages of a thermionic injector are all the things it does very well. It's a robust device. It is capable of very readily producing high currents. It's capable of operating for years. It has very low vacuum requirements. It doesn't require a drive laser, a very expensive subsystem to reduce the bunches. So it's simply a simple device that you connect up electrically and with microwaves. You don't have a big laser next to it that is part of the operation. Can run using a simple vacuum system rather than a ultra high vacuum system. It's basically much more than other accelerators like hydrogen physics. So the advantage was, for this application, it would have been a lot easier to put on a ship and do the job the Navy wanted to do.
Any questions more?
Are there any other questions?
So I guess that's the end of our Q&A section.
Okay, I'd like to show 2 more slides if I might then.
Okay, sir.
Basically, again, moving back to the NPSS, assuming you want to be a member, we have a program to help you become an NPSS member. There are currently, according to the IEEE database, about 8 NPSS student members at Sahrdaya College of Engineering Technology. If you're an IEEE member and would like to be an NPSS member, we have a program to do that. And let me see if I can blow that up. If you're already an IEEE or student or graduate student member for 2022, and this only really works if you've renewed your membership for the coming year, you can add NPSS membership for free. And many, many students in India take advantage of this program. I think we typically have more than 1,000 student members in India that take advantage of this program. You can simply go to the links on our student page. That's the page shown here on our website. And if you've already joined the NPSS, the IEEE, excuse me, you have a link to add NPSS membership. And if you haven't yet joined the IEEE, you can get free membership when you do join the IEEE, again, using the second link shown here. So I'd like to encourage you to do that. And that's my last comment. Let me just close this window. But we certainly welcome you to be IEEE members, and you can try out the society for free. Thank you.
Thank you, sir. So I think we are coming to the end of the section. And without a thanking note, an event is incomplete. So I take this opportunity to thank each and every one present here. Firstly, let me thank Dr. Steve for this great session. The session was indeed informative. So thank you, sir, for this valuable time with us. Thank you, sir.
Thank you very much.
Now let me thank each and every participant for your presence. Thank you all. Now, last but not least, let me thank each and every supporting hands behind this event to make this event possible. So thank you all. So link for the feedback form is given in the chat box. Please do fill it before the time limit. And that's the end of our section. Thank you and happy times all.
Thank you again. Thank you very much.